All right. Hello, everybody. Welcome back to Math Background for ML. So let's see. I think on Monday we left off somewhere around here where we were talking about maximum entropy and minimum relative entropy. So let me just make sure that I have Piazza where I can see it in case of people having questions. All right. We had some nice questions about entropy and information during and after last class. So let's go ahead and keep having those. And we'll start now with computing the Maxent distribution. So if you remember the Maxent distribution, we had fixed ourselves a vector of features that we were going to use for the examples. So if the examples were real numbers, that might be x and x squared. And we defined moments, which are the expected value of those features. We might want to construct a distribution with a particular value for those moments. So we might want to have the mean is equal to 4 and e of x squared is equal to 23, right? So the maximum entropy principle says that a reasonable distribution to take is the distribution out of all of the distributions that have that moment vector. There are typically going to be infinitely many such distributions. We'll choose the distribution that maximizes entropy. And why do we do that? We do that because maximum entropy means in some sense, it makes the fewest assumptions, right? So if you think about our friends Alice and Bob, if Alice and Bob agree on the distribution and Alice knows the sample and needs to send it to Bob, the expected length of the message to transmit that information to Bob is going to be the entropy of the distribution. The higher the entropy of the distribution, the more there is that Alice knows by knowing the sample that Bob doesn't. And so in some sense, every assumption that we make about the distribution would reduce the amount of information needed to transmit, right? It would constrain the distribution somehow. And so maximum entropy says make the fewest possible assumptions, pick the distribution with the highest possible entropy, leading to the most that Alice needs to tell Bob. And so we defined that last time around. And let's talk now about how we would actually go about computing that. In other words, if we know our set of possible outcomes, they could be, let's say, the integers 1 to 10, or all of the integers or all of the real numbers, but let's stick with a small finite set for now. So we know our outcomes and we know the features that we're going to use. Let's say x and x squared, right, or cosine x, or e to the x, right? Like there's a whole bunch of features we could possibly use, but let's say we fix a vector of features. And now what we'd like to do is figure out of all of the distributions over those 10 outcomes, the integers 1 to 10, and out of all of those that have the requested vector of moments, which one has maximum entropy. So in order to compute that, we need a few facts. And these facts are not at all obvious. Some very smart people figured them out and proved them. The proofs are mostly beyond the scope of this course, although there are future machine learning and statistics courses that you might find these proofs in. So what I'm going to do is I'm just going to state the proofs, state the facts without proof. You're not responsible for knowing the proofs. If you're interested, we can discuss them offline. All right, so the solution to the Maxent problem or to the minimum relative entropy problem, it turns out, this is the first fact I'm going to state without proof, it always has this form, that it's some distribution p theta of x, so capital X is our random variable, little x is a possible value of that random variable, theta is a parameter that we're going to have to compute later, and so we have a distribution p theta that has the following form. It's going to be p0 of x, so remember that p0 was our base measure for minimum relative entropy, times this thing, e to the t of x dot theta minus g of theta. So t of x, remember, is our vector of features, so each possible outcome, 1 to 10, has a vector of features. So 4 would have the vector 4, 16, which is x and x squared. We have two parameters that we've got to figure out, one parameter for each of those features. And then there's a function g that basically just ensures that this thing sums to 1, is a valid probability distribution. So this form comes up quite a lot, both because maximum entropy is useful and because it's what's called an exponential family distribution, and many of the common families of distributions that you'll see are exponential families. For example, normal, binomial, Poisson, all of these things are exponential families. And so this parameter vector theta is called the natural parameter, and that's to contrast it with the mean parameter, which is just the moments, the vector of expected feature values. All right, so that's useful, right? We don't have to optimize over all possible distributions. We just have to find a distribution of this functional form that constrains our computational problem somewhat. So even given this, though, there are a couple of problems that we have to solve in order to get to an explicit expression for the maximum entropy distribution. So the first one is this normalizer, right? So we have to figure out a functional form for that normalizer. And there's one functional form that always holds, although sometimes it's too unwieldy to be useful. But here's that form. G of theta is the log of the sum over all possible outcomes of this stuff, which is basically just everything but G of theta, everything but the G of theta term in this exponential family expression. And the reason that works is, we have this requirement that the sum of p theta of x has to be 1. And so if we write that out, right, the sum of p theta of x, this expression here is p theta. And then here, right, e to the a plus b is just e to the a times e to the b. So we can factor out e to the minus g of theta, right? Here we'll actually better to write this down. So we have 1 has to equal sum over x, p0 of x, x of t of x dot theta minus g of theta. We can factor this term, right? This is just exp of t of x dot theta times exp of minus g of theta. Then we can divide through. This doesn't contain an x, so we can pull it outside the sum and divide through. And we have that exp of g of theta is equal to sum over x, p0 of x, exp of t of x dot theta, right? And so this here, right, that expression is equivalent to this one here. All right, so that's an expression for g. It's basically the normalizing constant. And it's a useful expression, but it has a big summation inside it, right? Like it has the sum over all possible outcomes. And if the outcomes are the numbers 1 to 10, we can do that sum. If the outcomes are, let's say, 1,000-bit strings, not so much, right? So we might, in other circumstances, be able to simplify this expression somewhat, but for now, we'll leave it in its general form. All right, so now suppose we have an expression for g, maybe this one or maybe a nicer one. We have to find the actual value of theta. And remember, we're adjusting theta so that we get the distribution that has the given vector of moments. So we want e of t of x under the distribution p theta to be t bar. And again, stating without proof, it turns out that that requirement is equivalent to g prime of theta, the derivative, the gradient of g at theta, has to be equal to t bar. And so there's a few different things packed up in that equation. First, g is always smooth so that g prime exists, and g prime is always an invertible function in the sense that for any t bar in the interior of the achievable set of possible moment vectors, there exists a theta which makes g prime of theta equal to t bar. All right, so so that's sort of an abstract overview of how to solve maximum entropy problems. We're going to go through, we mentioned a bunch of examples last time, Bernoulli, Poisson, negative binomial. What I was, yeah, in a few minutes, what I'm going to do is go over in a little bit more detail one of these examples, just do a worked example so that you can see what this computation looks like. All right, and then I wanted to mention that so at the end of the first mini we talked about maximum likelihood, and we can do maximum likelihood to find, we can, given a family of distributions, we can, you know, with a parameter, let's call it theta, we can find the best theta to match a given sample by doing maximum likelihood. We also, like just earlier in this set of notes, described maximum entropy, which is we could compute the observed average feature value, it's called the empirical moment vector, which it's just 1 over n sum over all of our samples of t of that sample. And then we could pick a Maxent or minimum relative entropy distribution that has that mean vector. And it turns out we get the same answer either way, right? So maximum likelihood will justify this distribution, and so will maximum entropy. All right, so yeah, maybe now is a good time for me to do the example. So I'm going to do the example of a Poisson distribution. So what do I mean by that? So let's say that we're going to do maximum likelihood for the Poisson, right? So we have that we observe some samples, x1, let's say we just observe 2 samples, x1 and x2. Each one of them is in the natural numbers, or the, well, 0, it's in 0, 1, 2, and so forth. We have the probability of xi equals little x is equal to the Poisson likelihood, which is the Poisson probability distribution, which is, just copying this down, it's lambda to the x, e to the minus lambda over x factorial, right? So for now, we don't have to derive that. We just look that up in a table of probability distributions. And so what I'd like everybody to do, right? So, and then probability of both x1 and x2 is equal to the probability distribution of x1 times the probability distribution of x2, right? Because they're independent, their probabilities multiply. And so what we can do is we can do maximum likelihood. We can write down write out this probability distribution, differentiate it with respect to the parameter lambda, set the derivative to 0 to find the maximum, and solve for what is the maximum likelihood Poisson distribution, meaning the parameter lambda that makes the data as likely as possible if you sample it with that value of lambda. So what I'm going to do is I'm going to pause now, and this is, you don't need to hand in anything. This is just an exercise for everybody's intellectual benefit, I guess. But what I'd like everybody to do is to spend a little bit of time working that out. I'll pause for a few minutes and then I'll come back and work out the answer so that you can compare what you got to what I have. So I will see everybody back in a few minutes. All right, so let's go ahead and work out the answer for everybody. So if you haven't quite finished, feel free to pause and catch up in a sec. All right, so we have, here's our given information right here. And so what we'd like to do is want to maximize by setting the gradient with respect to lambda equal to 0. And just to make that easier, what we can do is take the derivative of log p instead of p. So we have that log p is equal to log p of x1 plus log p of x2, right? And the advantage, of course, of doing it this way is that we've got a sum of terms instead of a product of terms. And so this is equal to, just substituting this one in, right? So that will be x1 log lambda minus lambda minus the log of x1 factorial plus x2 log lambda minus log of x2 factorial. So what I'm doing here is I'm just taking this definition here of the probability of each x and taking the log of it. And so then, all right, we can differentiate and set to 0. So d log p is equal to x1 over lambda d lambda minus d lambda, right? For this term is constant, so it goes away. Then the same thing, plus x2 over lambda, that's a lambda, d lambda minus d lambda, and again that is constant, and so it goes away. And so for the gradient to be 0, we have to have, for all values of d lambda, it has to be 0, and so the coefficient of d lambda has to be 0. And so that says that 0 is equal to x1 over lambda plus 1 plus, sorry, not plus 1, that's a minus 1. Minus 1 plus x2 over lambda d minus 1, right? Those both have to be 0. And then we can rearrange, move the 2 over to this side, multiply through by lambda is equal to x1 plus x2. And so lambda is equal to x1 plus x2 over 2, right? So if you observe two samples from a Poisson distribution, x1 and x2, so x1 could be 3 and x2 could be 5. The maximum likelihood value for lambda, the parameter of the Poisson distribution, is just to set lambda equal to the mean of the two x's. So hopefully that is, well, it's a very reasonable way to set the parameter, because we can verify that in fact the mean of the Poisson distribution with parameter lambda is lambda, and so the maximum likelihood is telling us to do something very reasonable. All right, so if anybody has any questions about that derivation, please post them. In a few minutes we're going to have a quiz, but I want to finish this set of notes first. Actually, let's go ahead. We'll start the quiz now to give everybody as much time as possible. Yeah, I'll go ahead and start the quiz now. So I'm going to post on both Canvas and Piazza. I'll do Canvas first. All right, so it's now available on Canvas. I'll publish the link as well on Piazza. And we'll pause for a few minutes and come back once people have had a chance to work on the quiz for a little while. All right, so looks like most people have had a good chance to work on the quiz. So like I said on Piazza, even though quizzes are usually due half an hour past the end of class, which gives you the ability to be half an hour behind when you're streaming on YouTube. Because there's a bunch of new students this will be the first time that they've logged into Q&A, I wanted to extend the deadline to midnight tonight, 11:59 p.m. tonight, so that problems don't get in the way of submitting. So yeah, so feel free to continue working on the quiz. Just pause me and restart the lecture later. And for the rest of the lecture, I'm gonna finish this note and then start the next set of lecture notes. So just to I think it's important to get some practice with the idea of maximum entropy and exponential families. So to do that, this block here in the lecture notes gives just a few facts that we can prove about them. And so I'll go through those, and then I'll go through a longer example of working with Maxent. So the first fact, so we used, right, we gave the formula up here of p theta, right, this formula right here. And we used both p theta and p0, right? p0 is our base measure, p theta is the measure after parameter theta. And so there's a possibility of an inconsistency there, but in fact what I wanted to show was that if theta is equal to 0, you just get p0. And the reason for that, of course, is that here in this expression, if theta is 0, then t of x dot theta is 0. So this whole thing is just e to the minus g of theta. And that doesn't depend on x at all. And so since it's constant across x, it must be 1. So that the only thing that remains is p0. And so when theta is equal to 0, you get p0. So that's a nice fact. Another thing that we can prove, so we claimed above that picking theta so that g prime of theta is t bar, we claimed that that would give us the moment vector e of t of x is equal to t bar. And it turns out that that's not too hard to prove as well. So let's go ahead and do that. So we can start from the identity that 1 is equal to the sum over x p theta of x, right? Which is just equal to sum over x p0 of x, exp of t of x dot theta minus g of theta, right? And then we can differentiate both sides of that equality. So 0 is equal to the sum over x. P0 of x is constant with respect to theta. So by the product rule, we can just, by linearity, we just move the differential inside. Now we're taking the derivative of this part. And so by the chain rule, that's f prime. So the derivative of exp is just exp. T of x dot theta minus g of theta d, this thing here, right? So t of x dot theta minus g theta. Okay, so that's using linearity and an application of the chain rule. All right, and that's 0 is equal to the sum over x, p0 of x, exp of t of x dot theta minus g of theta. And then this thing here, the derivative of that is t of x dot d theta minus g prime of theta d theta, right? And so G prime here is a row vector, d theta is a column vector, and so their product is essentially a dot product as well. All right, so now we can recognize that this part here, that is just p theta of x, right? Sorry, this is, I'm gonna just erase that and start over because my handwriting's bad. P theta of x, right? Because you can just, compare it to the formula for p theta, and so we've got a copy of that. And so we can split apart these two terms. Sum over x, p theta of x, t of x is equal to, right, this part goes on the other side, sum over x, p theta of x, again that's p theta, again, just erase it and start over, p theta of x times g prime of theta, right? So this here, g prime of theta doesn't depend on x, and so p theta of x has to sum to 1. So this right-hand side is 1. Sorry, not 1. 1 times g of theta, g prime of theta. And this part here is the definition of the expected value of t of x. So this is e of t of x. Okay, and so which we have been calling t bar, right? So in fact, as promised, if we set g prime of theta, if we set theta so that g prime of theta is t bar, then we have e of t of x is t bar. All right, so that's just an example of doing a derivation using exponential families. It's kind of a cute derivation because, who would necessarily think of differentiating the identity that you have to sum to 1? It's also some good practice with differential calculus. As always, please continue to ask questions. I'm just checking. Let's see. Oh, somebody is asking what is t-bar. So good question. T-bar, so we defined it, I think we defined it up here. Let's see. So in the, yes, right, okay. So we have a probability distribution. That probability distribution is over a random variable x. X can take values in some set, let's say the integers 1 to 10. T of x assigns a feature vector to each outcome, so it could be x and x squared. So, 1, 1, 2, 4, 3, 9, right, so forth up to 10 and 100. And then t bar is just the expected value of that feature vector over whatever distribution we're working with. So t bar is called the moment vector. All right. So I wanted to also do an example of maximum entropy. So let's write that up. So let's suppose that we have a random variable x which takes values on the integers 1 to 3. And we take t of x to be just x, right? So the only feature we're using is the random variable itself, meaning that t bar is just the mean of x. And then we have the, let's take p0 of x to be a third, right? So the uniform distribution on x. And we're going to have this formula here for the solution of the maximum entropy problem. So what I'd like to do is work out how to what I'd like to do is work out how to set theta, our natural parameter in this expression, so that we achieve a given mean. And in order to do that, there's a few steps. So the first step is going to be to work out an expression for g prime of theta. Well, first for g of theta and then for g prime of theta. And then we can solve a potentially nonlinear equation to get the right value of theta. And so let's say that we would like to have t bar is just 2, right? So our we're going to try and find the maximum entropy distribution subject to the constraint that t bar is 2. And what I'd like everybody to do is to try and work out that problem by themselves for a few minutes, and then I will come back and work out the solution myself. So yeah, so let's go ahead and pause. Again, there's nothing to hand in for this. This is just for people to work on for their understanding. I'll give people a few minutes to work on it, and then I'll come back and show the correct answer. All right, so we're back. Let's work out the problem, right? So the problem was given these assumptions here, we'd like to work out the value of the theta, that achieves this value of t bar. And so first thing that we have to do is work out g of theta, and g of theta is by, according to this expression, it's equal to the log of p0 of theta, so sorry, p0 of 1, so that's 1/3 times e to the t of 1, which is 1 times theta, plus same thing for 2, 2/3, sorry, 1/3 is the probability of 2, e to the 2 theta, plus 1/3 e to the 3 theta. All right, so that's g of theta. Then we can differentiate. G prime of theta is 1 over this same expression here, which I'll just write as ... so that I don't have to copy it out again. And then we can differentiate in here. So the derivative of 1/3 e to the theta is 1/3 e to the theta. Plus, and then here the 2 comes out, so this is 2/3 e to the 2 theta plus 3/3 e to the 3 theta. All right, and then we would like g prime of theta to be equal to 2. And this is in general a nonlinear equation, so it might be hard to solve. But in this specific example, we can just guess that theta is equal to 0 and check it. And so if we do that, this expression here, e to the 1 theta, e to the 2 theta, and e to the 3 theta are all 1, because all of e to the 0 is 0. E to the 0 is 1, and so if we have theta is equal to 0, then that implies that g prime of theta is equal to 1 over 1/3 times 1 plus 1/3 times 1 plus 1/3 times 1 is 1. And then this part here inside the parens, again, each one of these terms, e to the theta, e to the 2 theta, e to the 3 theta, those are all 1, because theta, 2 theta, and 3 theta are all 0. Theta is equal to 0. And so 1/3 plus 2/3 plus 3/3 is just 2, right? And so that's 2. And so we've discovered that if we would like the mean of this distribution to be 2, we can set theta to be 0. Now, obviously, I picked this particular example so that I knew how to solve it by guessing and checking. More generally, what we'd have to do is solve the nonlinear set of equations. And next time around, we're going to talk about techniques for doing that. For now, I don't think that it's a good idea to try and start any additional topics. So let's end the lecture here, and we'll see you guys again on Monday.